What kind of a lens does this? Makes everything upright and smaller. It's thinner in the middle. This is a concave lens. We'll find the focal length. We've moved the bulb far away. We have the lens taped to some cardboard, and we project the light onto a screen. I don't get a small point. I get light that's spreading out. This is a diverging lens. If I measure the diameter of the lens and the large spot on the paper and the distance between them, I can figure out where these light rays have come from, or where they seem to have come from. We'll try drawing the ray diagram. The light rays from the distant bulb come in parallel to the principal axis. The outgoing rays diverge. The light shined onto a screen, and if I measured this distance, that would be the diameter of the large spot, and the diameter of where the light came through, and this distance from here to here. That'll allow me to do the geometry to determine where these light rays seem to have come from. I backtrace the rays to F, which represents a virtual focus. There is no light coming through this focus. Now let's say I measure the large spot on the paper to be 8 centimeters. That would make this distance 4 centimeters. And the diameter of the hole where the light came through, say, was 3 centimeters. That would make this 1.5 centimeters. If the distance between the screen and the cardboard was also 4 centimeters, then we can set up two similar triangles, one here and one here, and get the focal length. We can say that F over 1.5 is equal to 4 over 2.5. We get a focal length of 2.4 centimeters, but because it's virtual, we have to make sure that it's negative. Now let's see what happens when the object is moved closer to the concave lens. A light ray goes in parallel to the principal axis and refracts away as if it came from this virtual focus. This is a diverging lens. Another light ray that's easy to draw is the one that goes to the center. We draw this ray as if it didn't refract. It just goes straight through. These lenses are supposed to be pretty thin, and right in the center the two sides are quite parallel. So it does refract and then it bends back the other way here, just like we saw when we did the rectangular prism. My eyes intercept these rays and trace them back. The point of intersection would be right here. I would believe that the image is right side up, coming right from there. My eyes now trace these light rays back to this point. This is back traced. That's virtual. That makes this image a virtual image. Even though this light ray is actually here, real light there, this one is not, so it makes it virtual. Using our formula, we use the negative 2.4 centimeters for the focal length, and according to the scale, it's about 5 centimeters out to the object. And DI works out to be negative 1.62 centimeters. Negative because it's virtual. And if that's 2.4, yep, I'll go along with that. That's about 1.6. Now for the height of the image. According to this scale that I'm using, I get about 2.6 centimeters for the height of the object. Again, we're using the negative sign, negative 1.62 for the distance to the image, and about 5 centimeters for the distance to the object. And we get a smaller image that's upright, 0.84 centimeters. This is supposed to be 2.6, so it's in the ballpark. Now something interesting here is that no matter where the object is, the image will always be smaller, upright, and virtual. Let's take a look again. I'm bringing that lens far away and up close.